Okay, good morning. See, I'm gonna wait a second and see if we get a few more folks. How are you doing this morning? Not too bad. Cool. So we're gonna continue our discussion of work today. Um, okay, so let me uh, start. I'll mention one administrative issue. Uh, you should have grades for your quiz posted. There were a couple that I had issues with the file. I couldn't get your files open. Um, but uh, I feel like that worked pretty well. I'm sorry it took a fair amount of time to get it to look at the to look at them all, but I think it's good to give you some feedback on the process of solving problems compared to just doing stuff in the homework system. So I'm inclined to keep doing that. Did you find that that was useful, or what did you think of that? No, the Newton's Laws quiz is graded. It's just not synced in the Blackboard gradebook, but I'll do that shortly. Um, you should see your results for the component that was in Blackboard though. Um, did you guys like that? You prefer doing both? Okay. Yeah, I kind of prefer having different ways to see how you're doing because I don't. Yeah, no, same. I don't. I feel like it's worth it. It's more time for everybody, but I think it's worth it because it gives me a clearer picture of what's going on. I can give you some feedback. Um, if I was to do everything that way, it would just take. I think it would take too long. But I think a mix is seemed to work reasonably well, so I'll probably do that going forward. And I'm keeping that in mind in terms of for the final two. We'll probably do some kind of a hybrid where we'll have some questions through the homework system and some questions through through Blackboard or something like that. So I thought it worked fairly well. Just put a note. I'll ask the other group what they thought of it too, and we'll kind of proceed from there. But I just wanted to get some feedback from you, how you felt about that. Okay, uh, and we'll have a quiz on gravity. Probably I'll release it tomorrow, and then you'll have a few days and have it due perhaps Monday night. That way, if people run into questions, um, if there are issues, and it'll also give us a chance to remind you. Yeah, yeah, I think it's pretty good. I mean, it's a little bit in terms of it being logistically easy. Yeah, there were only a few students who had problems, or like for a couple of them were kind of blurry. I couldn't read them, or the file was just a weird format or something, and I couldn't get it to open. But I think for the most part, it's pretty good, and it gives me a better picture of how you're thinking about solving problems. So I'm inclined to do it. Uh, going forward. Uh, what was I going to say about that? yeah, like so I mentioned for other stuff, we can proceed with the same kind of format. I think that that would be useful for you too to get more feedback. Oh yeah, so we'll expect we'll have a gravity quiz probably something like release it on on Thursday and then do like Monday. That's my thinking. So anyway, that's administrative issues, getting you feedback. I feel like that's super important with the online thing to be able to give you some stuff that you can learn from. So I think that's really going to be important, and I'm going to try and do as much of that as I can, including I think lab reports are a good, or the lab is also a good environment for that, for giving you feedback. So let's see. Back to work. Or did anybody have any other thoughts or concerns about that, like quizzes, administrative issues? I would mention, I guess, in terms of grades, I'll have everything in Blackboard so you can see where you stand. And you've gotten the emails. We're kind of all getting the emails from admin in terms of how that's all going to shake out. I'm basically keeping a gradebook as I would normally keep a gradebook, so you can see in there what grade you would have, normally. Um, and then you've been made aware of the procedures, like in terms if you want to know what your quote unquote letter grade would be versus what the grading will be for this quarter. So I think that's the best way. Is just you can kind of see exactly where you are as I get stuff graded, being the one caveat to that. So any other questions or concerns? So okay, well let me know. Shoot me an email or reach out on Teams or something if you have questions about those issues. I wanted to revisit one problem that I think I did kind of a confusing job of explaining to you last time. And that was this issue. We had this problem with the guy hiking up the hill. Um, and it occurred to me that there's a better way to explain part of that. So I want to show you kind of a similar situation. So imagine, so this is kind of a similar problem. Imagine you have like a guy on a ladder. Um, And so this is a lot steeper than our hill example, so I think that this may make it easier to see how the angles work out. But suppose you have a guy on a ladder, maybe he's working on his roof or something and he's carrying something. And the ladder is making some, you know, small angle to the vertical. We would see that angle reflected here too. And the object that he's carrying, would have some weight. And he has to exert he or she has to exert a force on that object. Let's call it like, I don't know, the force to carry the object. That would be pointing up. And so the question, and like we did with the hiker example, the question is, how much work is the person doing? And questions, how much work is done by gravity? And so before I had I think I kind of led you astray by not being clear about what direction the force was pointing. So you can see the forces are in the y direction. The forces are up and down. And then the displacement is along the ladder. So let's look at the gravity case first, because in that situation the forces are both pointing down. So when we're thinking about the work done by gravity, so and let's imagine for a moment that the person is walking down. Sorry, let me just clarify here. So it's the end of the workday, or they're coming down for lunch or something, and they're walking down this ladder and they're carrying something. So if we look at the part where it's the work that's done by gravity, the force of gravity is pointing down, and the displacement vector is along the ladder. And so you have these two vectors, and there's this small angle between them. And so in this case, it's clear that if we apply our definition of work, F dot D, or FD cosine theta, the F is just mg, and the D cosine theta, well, if we look at this big triangle, D cosine theta would give you the part that's adjacent to theta, or the adjacent side of the triangle. And so D cosine theta would be the same thing as the height. And you can see also that, if you make the ladder more and more vertical, this D cosine theta would become the height if it's just up and down. And then that connects back with our example of, like the coffee cup, if you're holding the object up or down or whatever. So and then it becomes a one-dimensional problem. So that would be the work done by gravity. And initially, we were talking about this being negative. Well, in this case, the work done by gravity is positive because you're walking down the ladder. So both vectors are pointing down. Okay. So, and then kind of the other situation that we're considering here is the work done by the person. So in this case, and this is where we kind of got turned around last time. So the displacement vector is exactly the same, but the force, instead of being pointed down as well, the force is pointed up. Okay. And there are different ways that we can think about this. We can recognize that since they're both, since they're one's pointed up and one's pointed down, we could say immediately, well, this is negative mgh. And we know that F, and just to clarify here, if we look at the sum of the forces on the object, we have the carrying force minus mg is going to equal the mass times acceleration in y, but that's 0. So in other words, the carrying force is the same size as the object's weight. Now, since you could look at this and say, well, okay, they're in opposite directions, so therefore it's negative. But the one ingredient that I wanted to add to this is that we can also specify this in terms of the angle. So before, So before, here, we were looking at this angle, and this was theta. Let's call this one theta prime. So another way to think about this is to say, okay, well, this is also FD cosine theta, where now our carrying force is mg, but the d cosine theta becomes d cosine theta prime that I have here. And I think the thing I just wanted to clarify is the fact that theta prime plus theta has to equal 180 degrees. So you can state theta prime in terms of theta. Okay. So in other words, this is mgd cosine of 180 minus theta. And then if you look up in your trig identities, cosine of 180 minus theta is the same thing as negative cosine theta. So then this becomes also mg, negative mgh. So why I'm mentioning this is just because we had some discussion last time about, oh, you could add 90 degrees to something or something like that. This is the way I think you should think about it in terms of relating angles when you have these pairs of forces where one is negative and one is positive. This is the relationship that you want to take advantage of. So that was just a point that I think there was some confusion on that I wanted to revisit. Do you guys have any questions on that? Any questions? So on this kind of clarification here. So I could put in here that this is negative mg d cosine theta. Yeah, so this is, this is just our definition for work, FD cosine theta. But really the cosine theta in this problem, when the vectors are in opposite directions, is theta prime. So I'll just put here, this is the general definition. Uh, yeah, so mgd cosine theta, and then this d cosine theta is the same thing as height, so it becomes negative mg height. Negative mgd cosine theta prime. So this cosine theta prime, it's positive. This is positive. But when you evaluate theta prime in terms of theta, it becomes negative mg d theta, cosine theta. Or to put it another way, this cosine theta is an angle that's larger than 90 degrees. So we can find that in terms of theta, and when we do that, we find that the cosine is going to be negative. So yeah, you don't add the negative sign until after you've put, you can't pull that out until you've stated theta in terms theta prime in terms of theta, in other words. Does that clarify it for you, Caleb? Yeah, I think it's one of these things where it's kind of confusing because it's kind of deceptively simple. It works out when we keep track of the negative signs, but sometimes I find myself doing this. You kind of know what you expect. Whoa, this should be negative. So we may sort of skip around and actually make mistakes. Okay. I'll tell you what, if there are more questions about this, we can come back to this issue. I want to talk about a couple new things. Yeah, exactly. So it's kind of in all the gory detail to get that negative sign. I just wanted you to see where that's coming from because in our discussion last time, there was some talk about if you add 90 degrees to theta, that would fix the problem. But I was thinking about that, and that's not exactly what you want because, so suppose, with this situation, if you add 90 degrees to this angle, so if this is theta, if we add 90 degrees to it, you would get an angle that's like this, but you know that the real angle should be quite small. So it's not that you add 90 degrees, it's that you have to take 180 minus the angle that you start with. So yeah, it's a lot of discussion just to pick up that negative sign. Okay, so let's let's return to the dot product. I want to show you this in a little more detail and show you an application of it to an actual physics problem. Um, uh, so we've been talking about how the actual definition for work is F dot D, and we introduced this a little bit as it's a type of multiplication where you have two vectors and you get out a scalar. Work is a quantity. The units of are energy, and it's just an amount of energy. It's not. It does not have a direction, unlike forces and displacements. And one way you can think of this is as FD cosine theta, where now these are not the vectors per se, it's their magnitudes of the two, and then times cosine theta. And this cosine theta that we're talking about, it's the angle between them. So if this was F and this was D, it's this theta. And one way you can think of this as, or sometimes you'll see language describing this as a projection. You project one vector onto the other, and that determines the dot product. So like you think of this as like the part of this that's along the D vector. So you can see, if these are perfectly on top of each other, then you just get F D. But if they're perpendicular, then there's no projection, and so this F dot D would be 0. Let me be very explicit about it here. So a couple properties. I know you guys are. It sounds like people are seeing this right now. But just in general, some properties of the dot product. So it's commutative. This is not the case with the cross product. Another property is you can distribute the dot product. So for example, this is the same thing as A dot B plus A dot C. And let's show you this just in our IJK notation. So do you remember? So recall IJK unit vector notation. So you know that this corresponds to if you imagine a coordinate system where these unit vectors are vectors of length 1 that point along the different directions in the Cartesian coordinate system. So we can express the dot product in terms of the unit vectors, and you can see kind of this more like a regular, what we think of as multiplication. So if I was to express this in a general way, suppose we want to look at a general dot product between vectors A and B. We could write each of these vectors in terms of its components. So think of this as, it would be the component of x, or sorry, of A that's in the I direction, plus the y component would be in the j direction. The z component would be in the k direction. And similarly for B, now when we go to multiply these, something to keep in mind when we're thinking about the unit vectors. So if you have I dot I, recall these are of length 1, and they're pointed in the same direction. So it would be two vectors of length 1 along the x-axis. If you multiply that together, and you can think of this as 1 times cosine theta, where the theta is 0, and so cosine theta would become 1, and so this whole thing would just be 1 times 1 times 1. It's 1, okay? And this would be the same, for j dot j equals k dot k, or sorry, k hat dot k hat, and that's 1. So that's probably more detail than you want, or you're like, I get it. But this is just thinking about these vectors, the unit vectors, in this framework of the dot product. And then similarly, we can look at the, what if you have mixed unit vectors, so like I dot j? Well, we know from thinking about this, this would be, 1 times cosine theta. But if you're talking about the x-axis and the y-axis, the angle between these is 90 degrees. So this would become 0, and this whole thing then would be 0. So I dot j would equal 0, as would, I dot k hat, or I hat dot k hat, and of course, k hat dot j hat. And so if you want, so this is sort of the definitions, the thing that you need when thinking about the unit vectors. Now, if we look at an actual dot product between vectors that are expressed in terms of their components and unit vectors, it would look like this. So just, I'm not going to go through this a bunch of times, but I want you to see it at least once, kind of in all of its gory detail, just in case. And you're seeing this right now, or you've seen this in your math classes, yeah? So notice, you can imagine foiling this thing out. You would pick up, the only parts that you're going to pick up are ones that have the same unit vectors. The components where you're mixing unit vectors are going to go away because, as like up here, I hat dot j hat would give you 0 and all the other mismatched components. So you'd pick up from this ax times bx times 1 from the product of I hat dot I hat. You'd pick up ay plus by, or sorry, times by plus az times bz. So, and notice it doesn't have any direction because the unit vectors die when you multiply them by themselves. And all the cross components go away. So this is kind of the definition of the dot product written in our unit vector notation. And I suspect this is review, but I wanted to make sure that we go through it just in case somebody is less up to speed on that. So good. You've seen that before? And you've probably done a lot of problems with this. I'll show you. Tell you what, I'll show you one simple example, and then I'll show you one example with forces here. So for example, you can imagine, this is not, these should be dots here. Give me a little box for some reason. So you can imagine now doing this with numbers, just like you would do. So why isn't every term distributed with each other? So think about what would happen. So for example, ax I hat times by j hat, this is ax by I hat dot j hat, but like we said, I hat dot j hat, these are perpendicular, so this would be 0, and so this whole term would be 0. So all cross terms are 0. Does that clarify for you, Krishna? To put it another way, only the ones with the same unit vectors survive when you multiply them? Are you further questions on that point? Here, let me show you another. I'll show you an example, and then we can see if that helps with that as well. So let's just pick one of these because they're kind of very similar problems. But so a dot b plus c. So like I mentioned above, this is distributive. So you could, for example, look at the terms separately, a dot b plus a dot c, or we can add b and c together and then do that. Let's try it that way. So let's write this out. This will be 9.0 in the I hat direction minus 8.5 in the j. And then b plus c, we have negative 8 I plus 7.1 j plus 4.2 k hat. And then we're adding to that c. So c was 6.8 I minus 9.2 j hat. So the addition of the vectors is something that we had already sort of done in the context of Newton's laws, right? You could add forces together. You could add their, and you would do that by breaking them into components and then adding the components together. So this is the same thing. We're just provided with vectors that are already written in terms of their components. Let's see. So when you add this together, what are you going to get? Notice we have negative 8 plus 6.8. So this will be, let's see. Let me just add them first, and then we'll do the dot product. So the negative 8 plus 6.8 would be negative 1.2 I hat. The 7.1 and negative 9.2 would be negative 2.1 in the j hat. And then the 4.2k, there's only one k component, k hat piece in the z direction. So we'd have just the 4.2. And then when you go to do the dot product between these two vectors, the 9.0 would be multiplied by the negative 1.2. So that's negative 10.8. I hat times I hat would give you just 1. But 9.0 times negative 2.1 I hat times j hat, that would give you 0. The 9.0 I hat times 4.2 k hat would also give you 0. So in other words, you're only picking up the pieces that have the same unit vectors. So then the other piece that we would pull out of this is the negative 8.5j times negative 2.1j. So that would give you positive 17.85. You add this negative 10.8 plus 17.5, you end up with basically 7. Okay. It has no direction, right? Because this is a vector. The dot product takes two vectors and gives us a scalar. We've only picked up the components that have the same unit vectors in the dot product. Notice this 4.2k doesn't matter because the k hat component of the first vector is 0. You know, you can think of this as being like plus 0 k hat. So 0 k hat times 4.2 k hat, you get 0. And you could imagine doing these. I think you get the drift with this. You could imagine doing other questions like this, just like this. Does that clarify this for you, Krishna? Are you guys doing problems like this? I feel like the notation may be a little bit new, but once you get the hang of it, it's really not so. It's not so complicated. Now, what I want to do is show you this on an actual physics problem instead of just all that we've talked about so far is math, right? Like this is just A's and B's. It doesn't mean anything. And so let me show you an actual problem. Let's see here. 1 second. Crap. So here you go. Instead of A's and B's, we have an actual physical situation. So a 2200 Newton. Oh, wait. No, that's not the problem that I want. 1 second. Come on. Okay, here we go. So a force acts on a small object of mass 95 grams if the displacement of the object is d equals 5.0 I hat plus 4.0 j hat. Find the work done by the force, and also what is the angle between F and D. So now we're going to use this mathematical apparatus that we've been talking about in abstract to look at an actual situation where we find the work. So it's kind of tough, but I think it's useful to start with something like this where you draw a picture. So drawing in 3D is always a little perilous, but I'll do my best here. The force is 10 I hat, 9 j hat, 12 k hat. So it's sort of up here somewhere. You can think of that as, oh man, it's really 10. So 10 I hat, 9 j hat, 12 k hat. So let's think of the force as being as a vector that's going from the origin basically to this point. Oops. And the displacement is 5 I hat, 4 j hat. So that's a vector that lives in the xy plane. It has no z component. So it would be somewhere like here. Okay. So what we want to do is evaluate the work done and find the angle between these. Okay. So to find the work, we know that it's F dot D. So let's use this definition that we've just been talking about. It'd be 10 I hat plus okay. The only components of this that are going to matter are the ones that have the same unit vector. So we would pick up a factor of 10 times 5, so 50 plus 9 times 4, 36. So we would get 86. Notice this was in kilonewtons. So this would be 86 kilojoules. Okay. And then the second part of this is kind of interesting because it says, what is the angle between F and D? So we can calculate this angle. Ah, man, I'm having problems with the menu popping up. We can calculate this angle. So how do we do that? Well, we have evaluated this and we got a number. So we know what the work is. But we also know that this is given by the definition f d cosine theta. So in other words, we can restate this in terms of the magnitudes of the vectors and so does the mass not matter? It depends. It would matter if we want to find something like acceleration. But in this case, we don't need the mass to find the work. So this, and you'll notice this sometimes, it turns out this is an extra piece of information. I'm not going to say that you don't need that, you don't ever need it, because of course it depends, but I'll say it's an extra piece of information for this problem. So that's that speaks to problem solving techniques, and uh, sometimes you're going to encounter problems that give you more information than you need. And if you are accustomed to only having the exact information, it can really throw you for a loop. So I would keep that in the back of your mind that you can run into questions where there will be extra information. So if we're calculating work though, we just need F dot D. We don't actually need the mass. Back to this question of the angle. We calculated what the work is. We also know that it's FD cosine theta, so we can solve this for theta. So cosine theta is going to be the work divided by the length of these vectors. How do you find the length of a vector that's written like this? How do you do that? Yeah, good. You take the norm, which is another term for just, applying Pythagorean theorem in 3 dimensions here. So in other words, this would become 86 divided by the length of f would be the square root of 10 squared plus 9 squared plus 12 squared times the square root, or times the length of d, which would just be the square root of 5 squared 4 squared. And this would give us cosine theta, and if you evaluate this, you get 0.745. So if you want theta, you would take excuse me, you would take the inverse cosine of this quantity. So this would be the inverse cosine of this 0.745, which would give you basically 42 degrees. Okay. So this is, I think that I'm almost certain there's a problem in your homework that's like this, where you have to evaluate work. It's written like this. You have to find the angle between a couple vectors. So this is an example of how you go about doing that. Questions on this? So how do you get 50 in A? So the only components that are contribute are going to be 10 times 5, the 50, plus the 9 times 4, 36. So this 12, you can think of this as being plus 0 k hat. So this piece is 0. Oh, wait a second. Yeah, but that's just a typo. Sorry. This is I. Um, yeah. So work and speed. We have two things yet to talk about. This is the problem with this chapter is talking. We end up spending a lot of time talking about these mathematical ideas, but there's two things yet. One is if you have, so we're not going to, of course, have time to. Yeah, no, Krishna, I made a mistake. So this should have been I, like up here. So two things yet that we're going to talk about. That is varying forces. So if you have a force that varies, this F dot D is going to become an integral. So the integral of F, if this is a function, you can think of this as F as a function of D dot D. Um, and then the other thing that we're going to talk about, so this is basically section 7.3. And then the other thing that we're going to talk about is this thing called the work-energy theorem, which relates work and kinetic energy. And so when you talk about velocity, the kinetic energy depends on the velocity. So read the next couple sections. So this is in section 7.4, 7.3, 7.4, and we'll talk about it tomorrow. So because you'll need to be able to do a question like this in the homework, and you're going to need to be able to use the work-energy theorem. I could keep just talking, but I don't want to infringe on your time. If you have a course coming up. Yeah. Further questions? Okay. Well, thank you for your attention, and we will see you tomorrow. Yeah. No, this work kinetic. There's a whole section. It's pretty straightforward. Here, I'll just tell you real quick. So remember we had talked about like the net work. So it turns out that the net work is equal to the change in kinetic energy. So yeah, I can mention this quick now. It'll be useful for your for solving problems. So like this example where we had This example with the coffee cup, where we lifted the cup, and we found that, you do work on it, but gravity is also doing work on it, and they were equal. They had the same size, but one was positive and one was negative. So when you added them together, it was 0. Well, that was the case. You're just lifting an object. The object's kinetic energy didn't change. Yeah, so the work net is the change in kinetic energy, and kinetic energy equals 1/2 mv squared. Yep. Okay, yeah. So it's a lot easier to deal with if you're talking about energy, because energy is a scalar, right? So actually the calculations a lot of times are more straightforward because you don't have to worry about chasing down what directions everything is pointed. You're not working with forces, you're working with energy. So this is one of the things that makes this pretty powerful, because it connects together work with energy, and then if we're talking about energy, we can do a lot of calculations with it. So for our lifting the coffee cup example, the change in kinetic energy was 0. But you can imagine dropping the coffee cup. So suppose you drop it and it falls some distance. Okay. So in this situation, the work, you're doing no work. It's just mg. So this was, in this situation, it's just the work done by gravity. So and the work done by you is 0. So the work done by gravity would be the force times the distance. If it's just a one-dimensional problem and they're both pointed down, the force and the displacement, then this would just become m g d, and then this would equal 1/2 mv squared. So notice the mass doesn't even matter. You can then solve for the velocity. Velocity would be the square root of 2gd. And this is, notice this is the same thing as when we looked at this problem initially. You drop an object, v final squared equals v initial squared plus 2ad. Hey, there's no v initial, so v final squared would be the square root of 2ad. Well, what was a? It's gravity in this case. So this gives us a tool we can use. It connects with previous stuff that we've done, but now we're starting to get into energy. Does that help? I think that'll help you with the homework. Cool. Excellent. Yeah, let me know if you run into questions. We'll go from there. So have a nice day. I'm gonna sign off here.